Guys, today we are going to start off our Unit 1B notes by taking a look at something called the fundamental theorem of algebra. So in our notes packet on the very front page, it's asking us to give the degree of each function and then graph the function and state its x-intercept. So if we think about degree, remember if we have standard form, degree is just the largest exponent I see in my function. So our degree for this first problem would be 2. And then off to the side here, I've graphed that function for us. And I can see that I have an x-intercept here at -2 and at +2. X-intercepts are at -2 and +2. And I'm going to do the same thing for my next function. Notice my next function is in factored form. So for factored form, I have to add up those exponents. I have an exponent of 2, and here where I don't see an exponent, that would be 1. 2 plus 1 would give me a degree of 3. And then if I come to my calculator and take a look at my next graph, here's my function all graphed for me. I have x-intercepts at -3, and +1. And I am just going to make a quick note that we have quadratic behavior at +1. My next function has a degree of 2. We're back in standard form, so I'm just looking for that biggest exponent. And then if I look at the graph of x squared plus 3x plus 2, I've got x-intercepts at -2 and -1, -2 and -1. The next function in my list is in standard form again. My biggest exponent is 4, so that means my degree is 4. If I take a look at my graph here, x to the 4th, that's this guy. We've got x-intercepts at -1, 2, 3, -3. I have an x-intercept at 0. I have an x-intercept at 2. And I have an x-intercept at, this would be 2, 3, 4. At 4. A lot of x-intercepts for that one. My last graph for this first table, I'm in factored form again, so I'm going to add up my exponents. So that would be 1, 1, and 1 for a total of 3 for my degree. And then my graph that I have here has x-intercepts at -2, at +1, and at 2, 3, 4. So if I take a look at my degree for each function and my x-intercepts for each function, I notice that whatever number I have for the degree is actually the total number of x-intercepts that I have here. So where my degree is 2, I have 2 x-intercepts. Where my degree is 3, I have 1. And then for that quadratic behavior, remember that the multiplicity here would have to be equal to 2. So I actually count that 1 twice. So 1, 2, 3. Degree of 2, 2 x-intercepts. Degree of 4, 1, 2, 3, 4 x-intercepts. Degree of 3, 1, 2, 3 x-intercepts. Okay? So the degree is the same as the number of x-intercepts, including multiplicity, including where I have quadratic or if I had cubic behavior. So I'm going to put including multiplicity. That's actually a really important idea for algebra. That's what we call the fundamental theorem of algebra. Anytime you're in a class and you learn something that's called the fundamental theorem of the name of that class, that's a pretty good hint that's kind of important. So the fundamental theorem of algebra is what we're going to use a lot in this unit. And it's this idea that whatever the degree of my polynomial, that's how many roots I should expect to have. So if my function has a degree of 5, that means that I should have 5 zeros or roots or solutions. We've used a lot of, we haven't seen solutions yet, but roots, x-intercepts, zeros, we've used all those words sort of kind of interchangeably up to to this point. And that's the same idea that we're going to see moving forward. Whatever the degree of my function is, that's how many zeros or roots or x-intercepts or solutions, that's what we're going to get to in this unit. That's how many of those things I should expect to have. So I get another piece of important information from my function. I can use the degree this time to tell me how many solutions I should expect to have, or zeros or x-intercepts, whatever I'm looking for. So if we take a look at this box down here at the bottom, it says given the function, state how many zeros it should have, then graph the function and find its x-intercepts. So zeros expected, remember this is just going to be the same as the degree of our function. Okay, so for this first function, we've got 2 and 1. That would give me a degree of 3. Since we're in factor form, I'm going to add that up. So I expect to have 3 zeros. If I come over here to my calculator and flip forward to this function, I get 1, 2, 3 x-intercepts, 3 zeros, right? And my x-intercepts are at -2, +1, and +2. Fundamental theorem of algebra, this idea right here. For my next function, x squared minus 1 times x plus 3 squared, 2 and 2, add those up, I get a total of 4. So I would expect to have 4 zeros for this function. So if I flip forward to that graph, here's my function all graphed for me. Oop, I made a mistake on this one. Let me edit this really quickly. That should not be a cubed, that should be a squared. X squared minus 1, x plus 3 squared, that looks better. Okay, here we go. I've got an x-intercept at -3, but it's got that quadratic behavior, so it counts for 2. And then -1 and +1. So 1, 2, 3, 4. My number of x-intercepts matches my degree, matches the number of zeros I expect. Our next function's in standard form, so we get the degree from that biggest exponent. So our degree here is 2. Now let's take a look at this graph. X squared plus 3x plus 5. We don't have any x-intercepts here. I'm going to write down none. That's not what I expected to happen. I would expect to have 2 x-intercepts. So we'll talk about this problem here in just a minute. My next function, degree of 4. So let's take a look. Move forward to my next graph. This time I only have 2 x-intercepts. I don't have any quadratic or cubic behavior that's going to increase that. So this one also a little off from what we're expecting, but I do have x-intercepts at -1 and at 0. And then for our last function, factor form, so I have to add up my exponents again. There's 2, 1, and 1, so that would give me a total of 4. And let's take a look at this graph. I just flip to that next page. So we have an x-intercept at +1 and at 2, 3, 4, +4. Also not quite what I was expecting. I had 2 x-intercepts here, both linear behavior, right? So I know their multiplicity is just 1. So that's a little bit different than what my fundamental theorem of algebra told me. Okay, so do all of your functions have the same number of zeros and x-intercepts? The number of zeros I expected, not matching that number of x-intercepts for each of these. Okay, so let's talk about why. Why do I not have 4 x-intercepts here or here? Why did I have none for that parabola? So it turns out that the fundamental theorem of algebra, in addition from telling us that the degree should match the number of zeros, it gives us some other information as well. The number of zeros includes any multiplicities, which we already talked about. And then it also includes zeros that are non-real, what we would call imaginary zeros. So we're going to talk more about those in the future, but what that's telling me then is that for these functions where I had a different number of zeros that I expected versus what I got, that tells me that I've got some imaginary zeros happening there, okay? And again, we'll talk more about that in a future lesson. So it tells me that some functions have non-real or imaginary zeros, and that's included in my total. So that last graph that I looked at where I knew the degree was 4, but I only had 2 x-intercepts, that means that I would expect to have 2 imaginary zeros as well. And then the last piece of information that we'll talk more about when we talk about imaginary numbers and imaginary zeros is that if I do have imaginary zeros, it has to be an even number of imaginary zeros. And that actually matches what we saw on the last page. So for this function, we expected 2 zeros, but we didn't see any. That would leave me with 2 imaginary zeros. For our second to last function, we expected 4 zeros. We had 2 real ones. That means, again, 2 imaginary. And for that very last one on the last page in that table, again, I expected 4 zeros. We had 2 real, so that would leave me with, again, 2 imaginary zeros. So our imaginary zeros will always come in even numbers. Okay, so let's take a look at this one more time. State how many zeros each function has based on its degree, right? So total number of zeros will be based on the degree. And then find its x-intercepts. And then state, we're just going to extend this one more, state how many imaginary zeros we expect this graph to have. So if we take a look at x squared plus 4, that graphed over here for us, x squared plus 4, I expect, based on the degree, to have 2 zeros, but I don't see any x-intercepts. That means that I have to have 2 imaginary zeros. I don't know what they are yet because we haven't gone in depth in imaginary zeros. We just learned that they exist, but I know that there should be 2 of them. For my next function, x cubed plus 8, my degree here is 3. So let's take a look and see if we've got x-intercepts for this guy. X cubed plus 8, I've got an x-intercept at -2. So that's 1 x-intercept. That means that I have to have 2 imaginary zeros to get to that total of 3. For my next function, 2 and 2 gives me a degree of 4. So let's see if we've got any x-intercepts here. I've got 2 x-intercepts, it looks like at -2 and +2. So 2 x-intercepts leaves me with 2 imaginary zeros. And then for our last function here, standard form, our degree would be that biggest exponent. So our degree here is 3. Let's take a look at our graph. 1 x-intercept at -1. So 1 x-intercept means I have to have 2 imaginary zeros to have 3 total. Okay, and again, we'll talk more about those imaginary zeros, how to find them, how I know what they are a little bit later on. The last thing I want to take a look at for today is kind of a throwback to something we did in our first unit. So if I knew the x-intercepts for my function in our first unit, we could write a function in factored form based on those x-intercepts. Here, we can do the same thing with our zeros. So write a function that has the given zeros, assume the least possible degree. So we won't add any multiplicities unless we have a reason to think that I have multiples in my problem. And a leading coefficient of 1, okay? Then give the degree of the function. We can do that. So for my first function, it says my zeros are 3, 0, and -2. Remember that these I would see as x-intercepts on the graph. So I could use these to write a function the same way we used x-intercepts to write a function in our last unit. So my function would be x minus 3 and then x minus 0, or you could write it as x plus 0, that also works, or you could just write that as x. And then x minus -2 would be x plus 2. So there's my function. And then give the degree 1, 2, 3. Since these all have exponents of 1, my degree would be 3 here. I could also count up the number of zeros I see in my list. For our next example, I have 1, 1, 5, and 3. Since 1 is repeated, that means I can use an exponent here. Remember we talked about this with our x-intercepts. We said I would have x minus 1, and x minus 1, x minus 5, and x minus 3. Since I have the same factor listed twice, I can actually just write that as x minus 1 squared, and then x minus 5 and x minus 3. So there's my function. And again, I'm just leaving this in factored form. It doesn't say it has to be in standard, so I'm going to leave it in factored form. There's my function, and its degree would be 2, 3, 4. Okay, degree of 4 there. For our next example, my function would be x plus 3 times x minus 5 times x plus 4. And then I've got another factor of x plus 4 that I would get since I have this same 0 listed twice. Instead of writing that factor again, I'm just going to write this as x plus 4 squared. Then my degree would be 1, 2, 3, 4. And you could also count the zeros in your list. 1, 2, 3, 4. For our last example here, just 2 zeros this time. So I would get x minus 2 times x plus 1. And my degree would be 2. That's it for our notes for today. We will do some more practice problems in class.